Hello everybody, getting ready to do lesson 7.5 part 1 of pre-calculus math today. Here is my email, animated PowerPoint math video at AOL.com. And today's lesson, 7.5 part 1, you'll have 14 points that will go into your notebook, operations with matrices, and then we have 50 points here of classwork to do today. And let's go into our bell work, teachers, students. Today's bell work. Condense the expression to the logarithm of a single quantity. So make these single logarithm quantities here, students. Teachers, give your students about 5-6 minutes. Pause the video for 5 and 6 minutes. Okay, welcome back for your solutions for today's bell work. For 113 here, we got 3 times natural log 4 minus 1/3 natural log quantity, x squared plus 3. The solution for that will be our first step here will be natural log 4 cubed. Natural log 4 cubed. This will go up here as our exponent. Remember your rules for expanded logarithmic expressions. This constant out in front will become an exponent, and then minus our 1/3 now will again go over here, become an exponent here, 1/3 natural log quantity x squared plus 3 to the 1/3 power, and then further turning that into a single expression here. The minus here is the same thing as a fraction bar, so this becomes a fraction bar. Natural log bracket 64, 4 cubed is 64 over quantity x squared plus 3 to the 1/3 power. So this shall become that. And then down here again you have another subtraction here. So this will become natural log 7t to the 4th to the 3/2 power minus natural log t to the 5th to the 3/5 power. And then to further simplify this here using power of powers here, this would be a product of powers. Okay, so natural log 7 to the 3/2 power. This will become 7 to the 3/2, and then 4 times 3/2 will become t to the 6th power minus, and then again when we use the power of a power here, 5 times 3/5 will just become t cubed. So it'll be natural minus natural log t cubed, and then further simplifying, this will become natural log 7 to the 3/2 t to the 6 over t cubed. So this minus will become a fraction bar, and then again simplifying further, it'll be natural log 7 to the 3/2 t cubed. So using our quotient property here of exponents, this will become t cubed. Okay, moving on into our first notebook slide here today. Equality of matrices. So in section 7.4 you use matrices to solve systems of linear equations. There is a rich mathematical theory of matrices and its applications are numerous. This section and the next two introduce some fundamentals of matrix theory. It is standard mathematical convention to represent matrices in any of the following 3 ways. So the representation of matrices, a matrix can be denoted by an uppercase letter such as A, B, or C. 2. A matrix can be denoted by a representative element enclosed in brackets such as bracket Aij, bracket Bij, or bracket Cij. 3. A matrix can be denoted by a rectangular array of numbers such as A equals bracket Aij, which would equal this matrix here. We have this situation here, A, row 1, column 1, row 2, column 2, row 1, column 3, etc., etc. out here, row 1, column n. row 2, column 1, row 2, column 2, row 2, column 3, etc., etc., like that. So two matrices, A equals brackets Aij, and B equals brackets Bij, are equal when they have the same dimension. So they have to have the same m times n. So it'll be the same I times j dimension here, rows and columns, and all their corresponding entries are equal. So they are only equal when they have this situation here for your matrices. Okay, let's try an example here. Example 1, equality of matrices. Solve for A11, A12, and A21 and A22 in the following matrix equation here. So we want to know what A11 is, A12, A21, and A22 is. From this matrix here, what satisfies those descriptions? Because two matrices are equal, only when their corresponding entries are equal, you can conclude that A11 is 2, A12 is -1, A21 is -3, and then A22 is 0. Okay, so this is a row 1, column 1, a row 1, column 2, a row 2, column 1, and then a row 2, column 2, which is what these terms here correspond to these descriptions of a matrix. Okay, so let's go into an example here. Find x and y, or x, y, and z in these matrices here. So x, -7, and then 9, and y equals 5, -7, 9, and -8. So when we're filling in here for our two unknowns there, we're saying basically that x equals 5, so x equals 5, and then y equals -8. Those are the corresponding positions there. And do I do this independent practice? I do. So x in this case would be 13, and then y would equal 12. So they correspond in the same positions there from this matrix here. Okay, page 8 here. Be sure you see that for two matrices to be equal, they must have the same dimension and their corresponding entries must be equal. For instance, this bracket here, this matrix here, 2, -1, square root 4, and 1/2, is the same thing as 2, -1, 2, and 0.5. But 2, -1, 3, 4, and 0, 0 do not equal 2, -1, 3, and 4. You just cannot discount this third row here. Matrix addition and scalar multiplication. You can add two matrices of the same dimension by adding their corresponding entries. Definition of matrix addition is if A equals bracket Aij and B equals bracket Bij are matrices of dimension m times n, then their sum is m times n matrix given by A plus B equals A bracket Aij plus Bij close bracket. So there's the technical description for matrix addition. The sum of two matrices of different dimensions is undefined. You cannot add two matrices of different dimensions. Okay, so let's try one here. So, for example, addition of matrices, we have these two matrices here, -1, 2, 0, 1, plus 1, 3, and -1 and 2. What does that equal when you add these two together? So, -1 plus 1, so we're going to move this one over here. We're going to add these two together, and then 0 and -1. And then here we have 2 plus 3, and then 1 plus 2. So that would be your first step here in adding matrices. They're the same dimension. They're 2 by 2, so they can be added. And then once you add these different positions of your matrices together, this becomes 0, this becomes -1, this becomes 5, and then that one becomes 3. So that'll be an addition of these two matrices here. And then B here would be 1, -3, -2. This is a column matrix, and then plus -1, 3, and 2. So how would we add that? That would be 0. So 1 and -1, 0, -3 and 3, -2 and 2. So the addition of that would be 0, 0, 0. And then the sum of 2, 4, 1, 0, 0, -1, and 0, -1, 1, and 3. So this is a 2 by 2. This is a 2 by 3. So what would that be? It's to be undefined because A is dimension of 2 by 3. This is a 2 by 3. And then B was a dimension of 2 by 2. So you cannot add matrices of different dimensions. Cannot do it. Okay, so let's try this one here. Find, if possible, A, which is A plus B, and then B would be A minus B. So this continuation of A, I'm sure this continues down. And then C would be 3A, and then D would be 3A minus 2B. So this is a 4-part problem here for A and B. So for A up here, use matrix capabilities of a graphing utility to verify your results. So by now, teachers, you should have shown your students how to use a graphing calculator to add matrices together. But we're going to go ahead and do it today as an example. A plus B here, here's our A, and then here's our B. And then this is your dynamic here of how you show your addition, your combination here of your corresponding entries from one matrix to another matrix. You have that situation there. And then I'm going to let you finish it, students. In operations with matrices, numbers are usually referred to as scalars. In this text, scalars will always be real numbers. You can multiply a matrix A by a scalar C by multiplying each entry in A by C. So the definition of a scalar multiplication would be if A equals bracket Aij is an m times n matrix and C is a scalar, then the scalar multiple of A by C is the m times n matrix given by C times A would equal CAIJ. So that would be the technical definition of scalar multiplication. So let's try one of those right now, okay? So scalar multiplication for the following matrix, find 3A. So we're going to multiply 3A, which, let's see how that's done. Okay, so 3A would equal 3 times A here. This is out front here as a general multiplication of our matrix. Then when we do that, here is our original multiplication. It would be 3 times each of the entries there, 3 of each one of these members of that matrix, and then when you get through multiplying out, you end up with this here as your product of that multiplication. So let's try one now. So we're gonna do C and D now of 15. 8, -1, 2, 3, -4, and 5 for A. Then B, 1, 6, -1, -5, 1, and 10. So C here would be 3A. So we're going to multiply 3 times A here. So when we do that, we multiply 3 times 8, 3 times -1, 3 times 2, 3 times 3, 3 times -4, and then 3 times 5. And we come up here as our product up here. That would be our product of 3 times A. And then for D down here, 3A minus 2B. So do I do this? I don't know. I'm not sure. I'm going to let you do that. So go ahead and finish that, students. Let's go on here. The symbol -A represents the negation of A, which is the scalar product of -1 times A. Moreover, if A and B are of the same dimension, then a minus b represents the sum of a and negative 1 of b. That is, a minus b would equal a plus the negative 1 of b, subtraction of matrices. The order of operations for matrix expressions is similar to that for real numbers. In particular, you perform scalar multiplication before matrix addition and subtraction as shown in example 4. Moving on now into example 4, scalar multiplication and matrix subtraction. So for the following matrices, find 3a minus b. So 3a minus b. Those are two matrices. Note that A is the same matrix from example 3, okay, where you found 3a. So we already know what 3a is. 3a minus b here, so perform scalar multiplication first. So when we do that, here's our 3a here, and then our negative of b is here. So here are our setup here for a subtraction problem. So when we have that, we're going to subtract corresponding entries from the previous page there, and then we end up with this matrix here. And let's try one now. So we have D here. We're going to do the operations with matrices D, 3a minus 2b. Use matrix capabilities of a graphing calculator to verify your results. So you should get into a kind of familiarity of using your graphing calculator to do matrix operations. So here's our A and here's our B. And we're going to do 3a minus 2b in this guided practice here. So up here, 3a minus 2b. So our first step would be 3a. We're going to multiply, but that wouldn't be it though. 3a here, 3a would be 24, then 2b. Okay, so multiplying across here, this would be your solution here, is what it would be. So the thing to do here, students, is to fill in your blanks here. I don't think I filled in those blanks for you. I want you to do your 3 times a, which would be down here. You have a 9 there, so you know that's where that came from. But then 2 times b here. This is what you should get as your solution here. So that's where you end up, but how did you get there? So do your multiplication and then your subtraction, or your 2 times b here, and then you'll end up there. And that is your 7.5 part 1. And here is my email, animatedpowerpointmathvideo@aol.com. And then for solution PowerPoints, classwork sheets, homework sheets, solution PowerPoints, any other course material, email me there. Thank you very much.